Hi guys, we're Group C. We're going to be presenting on a prosthetic surfing leg. I'm Shania Navarro.
Yoni.
Eddie Kubel. Tiana Rinaldi. So our bioengineering problem is a prosthetic leg for surfers. Right now, prosthetics are kind of targeted around basic functions and not really active ones, especially specific ones like surfing, so we wanted to bridge that gap. Our device also, we wanted to make it adjustable in height. For kids growing up, they have to get constant amputation upgrades, so we wanted to build a device that can be adjusted as they grow. Below the knee amputations are the most common, with about 150,000 per year. 93.4% of them are due to vascular diseases, mainly diabetes. Right leg amputations are more common than left, probably due to dominance. There are more right-handed people than left. Other causes for people who don't have limbs are congenital causes and accidents. Surfing is a high-activity sport which requires flexibility, range of motion, and ability to handle high impacts. So our prosthetic can fix that issue.
So in terms of surfing, a lot of the important motions are the pop-up. So when you're lying down on the board and you have to get up again, it's important to gain your balance both with the hind leg, with your back leg, and with the front leg leaning forward. The dominant leg is usually put in the back and it's used for steering, with the non-dominant in the front used for maintaining your balance. And so, and in terms of the motion of the lower leg, your ankle is definitely used to pivot in order to maintain balance and also to steer with the fins of the board.
So our design solution for the problems that we previously mentioned are to make an adjustable pylon prosthetic leg that allows 2 degrees of freedom, a rubber sole for traction, and that's affordable.
One of the only really mass-produced feet or prosthetic feet on the market for surfing specifically was the Swell Surf Foot, which attaches to any existing pylon basically. The treads on the bottom allow for increased traction, and the high surface area is good for balance. And several degrees of flexion with this particular foot were possible, which made it a pretty decent candidate. Other products out there are not necessarily designed for surfing. Like this foot, for example, the Rush Foot H2O, had desirable qualities that we're looking for, like the flexibility, the waterproof aspect, and also the traction. But in terms of surface area, it's pretty thin, so the balance might not be the best. And, a similar thing with this product, where it's not specifically designed for surfing, the Oser Veriflex, but it still supports high impact activity, and the material such as carbon fiber was something that we were looking to utilize for the flexibility and the durability. And the split toe design in this case was it helped with balance, and that was also something we were trying to look to try and incorporate perhaps.
So these are 3 problems encountered by amputees. These are some quotes from some articles. So for Mike Coots, he's a shark attack survivor, and he feels that the wood and metal prosthetics, he couldn't really get a grip on how to surf with them, and he feels that the carbon fiber is much better material, and his brain can actually stimulate and use the carbon fiber to steer the board. So that's what we incorporated in our design. Colin Cook is also a shark attack survivor, and he went from being an amputee to actually adapting to the surfing leg and being able to win the USA Surfing Championships. And the third account is from Dr. Jeffrey Kane, and he's a plane crash survivor, and he wonders how he can afford prosthetics as insurance only pays up to $1,000 a year, and our prosthetic costs less than that, but we'll get to that analysis later.
We went to the Long Beach Surf Shop owner, Long Beach Surf Shop there, and we interviewed the owner of the shop, and he walked us through the motions of surfing so that we could get a good sort of gist of what we needed our prosthetic to perform. So he told us about how usually the right or dominant leg is put in front and that, or put in back for balance and to sort of guide the person around, like across the wave. And in the rare cases where the left foot is dominant, it's called a goofy foot. But yeah, we used his interview to really gauge how the person moves while surfing.
We also spoke with a certified prosthetist at a hangar clinic, which is in Oceanside, New York, American New York, I apologize. And basically, like, her opinion about adjustable pylons was that they're usually really only used for fittings, and they're not necessarily safe for everyday use, which was kind of part of the inspiration to like create a device that could be used for like everyday and even in high impact activities that was adjustable. And something that also came up again was the affordability of these prosthetic devices and how it's usually a common issue and how people have problem affording it and how insurance companies, especially in the past, had a big problem with providing people money for them. And another interesting fact was that was the emotional effects that people often experience and how people who might lose a limb can equate that to like losing a loved one, and especially when they lose something important to them, like being able to do like rock climbing or surfing in this case, obviously. So it was definitely important to create a device that was functional and definitely got like restored the function as much as possible to somebody who would want to continue these activities.
For the specifications of our detailed design, we wanted to make sure that our prosthetic can withstand loads of 1,000 newtons and hopefully 1,250 newtons. This corresponds to approximately a person weighing about 100 kilograms to 127, which is a lot, but we wanted to make sure that the prosthesis is not going to collapse under nobody's weight. Also, we wanted to make sure it's ocean waterproof. Obviously, this prosthetic is meant to be mainly in the water, so it's important that every material will be durable and being compatible with the environment. We also wanted the prosthesis to have about 5 to 10 year lifespan. So this is the lifespan of an average lower limb prosthesis. And in our case, we are dealing with an extreme activity, but we still want to the prosthesis to last as long as a regular one for the daily basis. Also, the ankle component of our prosthesis is meant to have 2 degrees of motion. This will be in conformity with the motion that surfing will take, which is side to side, forward and back. We're focusing on these two. And also, after doing some testing that we'll mention later, we concluded that our design will have like a 20 degree range of motion. For the standards that we use for our prosthetic, we make sure that it is following the FDA guidelines. The first safety standard has to do with the structural loading of the prosthesis. We want to make sure they can withstand every load, static and cyclic load, static having to do with the body weight, cyclic more with the waves. Make sure it doesn't collapse. Also, the second safety standard is more focused on the ankle part and the foot. And lastly, we wanted to make sure that each prosthesis is unique to each amputee because every amputation is different in terms of morphology, height, or even the age of the person. So those are the ones we base on, besides the biology, the biological evaluation, which tests if it's compatible with the skin of the person, and as well as the materials don't cause any environmental issues. So these are the individual design concepts. On the left is my own sketch. So I focused on creating an adjustable pylon that is able to fit different age ranges. I also initially thought about having a ball and socket ankle, as well as a silicone socket to hold the residual limb.
for my individual design, I did an above the knee prosthetic, and the part that we carried out into our overall design was the textured rubber layer on the bottom of the foot for traction, especially with surfing. The water can compromise the grip.
So my individual design featured a ball and socket for the ankle, as well as a locking mechanism such as that's used for steer, to lock the foot with the board. Ultimately, we didn't end up using these designs.
And my initial design also incorporated the ankle component with the spring and almost like lattice accordion structure, as well as the top of the foot, which was going to provide both stability for the ankle and also some flexion.
For our decision matrix, we selected the criteria that we thought was most important: the saltwater proof, mobility of the ankle, durability, since it's going to be in contact with the ocean water, adjustability, security, and we evaluated from a score of 1 to 10 each member individual design. The purpose for each criteria was, as I mentioned, saltwater proof, because that's the environment that is going to be in most contact with. Mobility, because we want to make sure that the ankle does perform the necessary movements for surfing. Durability, as I mentioned, because it's an extreme sport and we want this prosthesis to last as much as a regular prosthesis. Adjustability, because surfing is a sport that has a lot of different ages. It has a big age range, so as much as a 7-year-old child, as much as a male adult or female adult could practice this sport, we want to make sure we can accommodate all of these. And also security, we don't want our prosthesis to collapse due to some wave or in the middle of the ocean. That's definitely dangerous.
So here's our decided design. We incorporated concepts from each one of our individual designs. So from top to bottom, we used the screwing mechanism from Gianna's design, from the socket to the pylon. We used the adjustable concept for the pylon from Mariana's design. We used Yanni's ankle design for our final, and the rubber layer from mine. We also incorporated a clamp to secure the pylon once it's at its adjusted height.
So this is the full assembly of our design constructed in Fusion 360. The full height has about 61 centimeters. We can see that at the top we have the socket that will hold the residual limb of the amputee. Then we have an adjustable pylon, as I mentioned. So the minimum height that the pylon can have is about 23 centimeters, which is the average height. Nice. Which is the average height of a 7-year-old child's tibia, and the maximum is about 35 centimeters, which is the average height of a male adult. The clamp, as we can see, is just meant to hold this height in place, make sure that it's not going to move while the person is practicing the sport. The foot has an open design concept. This way it's going to be lighter, offer less resistance to the waves. The ankle, we're going to go into each component with more detail, but just briefly, the ankle will have the 2 degrees of motion and have a stiff spring in the middle, and then specific textured sole that will be able to grip the surfboard. This is just an exploded view of our design as well as an animation, so you can see how everything is put together and screwed together. There should be a screw connecting the socket and the pylon, and the pylon to the ankle. For the pylon components, as I mentioned, but just a few more details, we have a sliding mechanism, so the outer tube will have approximately 6 centimeters and the inner tube will have 5 centimeters. The way it works is there will be a spring that would basically stop the pylon a spring that transverses the pylon and will stop it from completely separating or going over its maximum height. And then once the specific height is established, we just add the clamp to secure it in place. As I mentioned, it has approximately 23 to 35 centimeters in height, depending on what the person wants to tune it with. And the main material is stainless steel for both the pylon and the spring.
So for the ankle component, as much as we have mentioned degrees of freedom and it being mobile and capable of rotating and everything, for a regular person or an organic ankle, it's also important to limit that mobility. So this ankle component does that with that lattice structure that Yanni mentioned before. So this, while it is a spring in the middle, it is very rigid, so there's going to be minimal compression, and therefore the person won't really be able to sort of sink into the spring, but if they will have those degrees of freedom that we mentioned before. And we made it out of carbon fiber to also provide some sort of elasticity or flexibility. So for the foot component, the rubber sole again for tread with little balls to increase surface area to again maximize tread. Carbon fiber for that little ruby part on top to again try to have some sort of flexibility while the person moves with the ankle component. And
So we were able to make a physical model, as you can see here. It's not exactly adherence to like the initial design, but in terms of like the top structure is like similar, and the lattice with the spring. So the pylon would be adjustable and can be set to different heights. The lateral spring we weren't able to incorporate it just in this model, but again, this is just a model. It's not necessarily a prototype, so to speak. And the socket we didn't include because sockets need to be made custom fit to every patient. So the socket in the design is more just a placeholder in terms of what would actually be the case in practice.
So I'm going to go in more detail of the safety standards that we use and the actual tests that we performed. So as I mentioned before, we did structural loading. So we basically analyzed the body weight of the person, also forces at a certain angle, so to mimic the position of the person as they're doing the surfing. Also, mimic the forces of the waves hitting our prosthetics. So that was our first safety standard. The second one was more focused on the ankle component. So we wanted to make sure that it did have the 2 degrees of freedom and it wouldn't collapse and still be safe to use. The third safety standard had to do with being unique to each individual. We wanted to make sure that it is adjustable, even if it's due to the fact that it's a child growing up, or if the amputation stump is changing, because that could happen, and then therefore the height will change. We wanted to tune it to, this is not going to be for cosmetic purposes. We wanted to tune to being perfect for the extreme activity of surfing, making sure it's durable, and the materials don't cause any hazard to the environment. Oh, I failed to mention that, sorry. So this prosthesis can be recycled and reused, and that's one of the reasons why it's not supposed to be as harmful for the environment. And for example, the silicone that we're using doesn't produce any microplastics, so that will be again, for the biological standards, make sure that it doesn't irritate skin, Um,
So we did some simulation testing in console, and we did this on the ankle component and the pylon components, and we placed our wish force of 1,250 newtons downwards on the ankle component, and we found that it was able to withstand this force as it passed the factor of safety test as the value was greater than 2. We also performed this test putting the forces at opposite sides of the component, and we had the same result where it passed the test. And for the pylon, we did the same test. We had the bottom fixed to the floor, and we put a force of 1,250 newtons downwards, and it also passed the factor of safety test. And then we also did this for the sides of the pylon, and it also passed. So the performance evaluation was that all the components passed the test, and they withstood vertical and horizontal forces of 1,250 newtons. And the downward forces were to simulate a person standing on the prosthetic, so their body weight, and the side forces were to simulate if large waves crashed on the prosthetic and it would survive. Additionally, for the performance evaluation, we found in console that the rotation took place in the angle at 20 degrees, which is what we preferred, and we concluded that the ankle and the pylon both exhibited deformation in the same range, and that the components wouldn't fail, they would just move slightly. So some safety and risk analysis was that a large wave could come crashing snapping the clamp, and this would cause the pylon to fall to its lowest level, making the user's other hip hurt. But we feel that this would be a minimal possibility, as there would be a warning at each telling surfers not to surf in this very hard type current. Additionally, we thought that big waves can also make the ankle over-rotate. We accounted for that in the console simulations. But what would happen if this failed was that the prosthetic would fail in compression and the ankle would snap, freeing the springs, but this is very unlikely. We also had to take into account that the metal parts, such as the screws and the springs, could corrode or oxidize. This is also sped up because the ocean has a large pH, and this is unlikely as the user would probably replace the prosthetic before this had a chance to happen. Another safety risk analysis is that the bottom of the sole of the foot could become worn down over time, creating a slippery surface in between the board and the foot, making the user fall. But this is unlikely as it's used less than an everyday shoe, and again, the prosthetic would probably be replaced before this chance to occur. For the last safety and risk analysis is that the spring can overstretch. This can happen with poor storage conditions. So something can latch onto the spring when the prosthetic is stored, causing permanent deformation, which would lead to limited control of where the ankle movements take place. But with proper care, this is unlikely to happen.
So we came up with 2 bioethical issues that could occur. So there are some issues with all prosthetics in general with the skin to socket interface, which could cause irritation, ulcers, atrophy, and necrosis. Although we decided that someone would rather have a prosthetic than have to face these issues, as again, the pylon's adjustable, and it could make up for that issue with necrosis and atrophy. Also, within the sports industry, I guess, there's issues with, instead of bridging that divide between someone who does have a leg versus that doesn't, they think that it's going to provide an advantage rather than a balance. So that's occurred in like leagues like the Olympics, but again.
Yeah, so the cost analysis, basically the total cost of manufacture we found would be around like $465, with the total cost of the customer of around $800, which is relatively inexpensive compared to other existing prosthetics out there. So we thought that that was a pretty good margin.
This was our timetable. We completed it on time. We're here.
Yeah, and for the limits and constraints, the pylon, like, there's limited height and, like, you know, for the minimum maximum, so, like, if a taller person needed to use this, it might not necessarily work, and then once the height is fixed, like, you know, it's not going to move. For the foot, it's constrained kind of by the architecture of both the top and the ankle part, and the ankle again is limited to 2 degrees, and it's very rigid. So it's a limited range of motion.
So we learned a lot of lessons while doing this project. Number one was what materials we use for what components, because obviously the pylon needs to be strong enough to handle the weight of a person and waves coming at it in a different direction. But also the ankle needs to be able to move and have that flexibility while also limiting its range of motion in certain directions and situations. So that was important. The complexity of prosthetics, obviously there's different components and different ways to go about designing each component, and how we needed higher impact but also higher range of motion. The prosthetic has been.
Thank you, Dr. Guzman, for all your help with everything. Thanks to the Long Beach Surf Shop for their information, and Susan Wisla at Hanger for speaking to me, and Raul, he helped us with all our 3D printing, and my dad helped us actually build this. So